Now let's see the mode of operation for the evaluation of this connection formulae. Here also we rely on the Schrödinger's equation, which is the Bible in quantum mechanics, and we propose to exactly solve the Schrödinger's equation in the case of these problems that include these classical turning points. The mode of operation is like this. We have WKB solution written for system occupying region 1 and region 2, and that solutions will be representing the system or the object under our study in this region as well as in this region. In a mathematical approximation, we can consider these two regions are regions far away from the classical turning points. In a graphical manner, once you have an exact solution representing the system at a point extremely closer to the turning point, which will be generally a curve, then the solution representing the system in region 1 in this regime may be taken as an asymptote to the curve at the classical turning point. This argument is true in the case of the WKB solution in this region 2 as well. The curve representing the WKB solution in region 2 can be very well taken as an asymptote, that is a tangent at infinity, for the curve or the exact solution written for the system at a point extremely closer to the turning point. So we will be making use of this mode of operation in order to identify the connection between the two possible WKB solutions representing the system in the two regions. So the operation is like this. First of all, we will have to formulate the Schrödinger's equation representing the system at a point very closer to the turning point or at the turning point. It's an approximation procedure. You cannot write it at exactly the turning point. You will be writing it at a point extremely or infinitesimally closer to the turning point. Once you have an exact solution for such a Schrödinger's equation, you can draw the asymptote at infinity in the negative infinity regime or in the positive infinity regime. That asymptote in the negative infinity regime will turn out to be the WKB wave function representing the system in region 1, and we will see that it's an oscillatory solution. Whereas in region 2, this turn to be identical with the or exactly equal with the WKB wave function representing the system in region 1. So we have to formulate first of all the Schrödinger's equation near the turning point. This also we have seen during the derivation of the WKB wave function, that is being written in terms of say phi d square phi by dx square plus p square by h cross square phi equal to 0, where p equal to root 2m into e minus v. So p equal to square root 2m into e minus v. That include this term say potential energy v. This potential v of x, an arbitrary choice of x, v as a mathematical function of an arbitrary choice of position x, can be written in terms of the potential at the turning point x1. x1 is the turning point as we have taken earlier as well. In terms of a Taylor series expansion, v of x equal to v of x1 plus x minus x1 dv by dx at x1 plus x minus x1 all square over 2 factorial d square v by dx square at x1 plus etc. But we know that at the turning point, the potential energy V and the total energy E are exactly equal, so that V at x1 may be written as the total energy E itself, plus x minus x1 into dV by dx at x1 will be a constant V. Label it say C. Then p square equal to 2 mu into e minus v equal to 2 mu into e minus, instead of v we substitute this one. So e minus e vanishes. You will have a minus c into x minus x1. That minus is taken out. Minus 2 mu c into x minus x1 will be an approximate value of p square. Of course, the higher order terms are there, but we assume that we are satisfied with this accuracy up to this one, since x is an extremely closer point as long as x1 is concerned, or x minus x1 is infinitesimally smaller. Then the higher order terms will have the square and cubes of x minus x1. As x minus x1 is infinitesimally smaller, its cube, so fourth power etc. will be largely falling, and we assume that those terms are of no significance as long as p square is concerned, or the magnitude of p square is concerned. So p square equal to minus 2 mu c into x minus x1. You substitute this value of p square in the Schrödinger's equation, it get modified as d square phi by dx square minus 2 mu c by h cross square into x minus x1 phi equal to 0. Now we substitute 2 mu c by h cross square raised to 1 by 3 into x minus x1 equal to zeta, so that the variable shift from x to zeta. Clearly d zeta equal to 2 mu c by h cross square raised to 1 by 3 constant. X minus x1 upon differentiation give you dx minus derivative of x1 is 0, since x1 is a constant whereas x is arbitrary. So d zeta square we have to substitute for dx square. So let me square it. D zeta square equal to 2 mu c by h cross square raised to 2 by 3 dx square. And once we shift the independent variable from x to zeta, the wave function phi of x transform to psi of zeta. Then d square phi by dx square may be written as d square, instead of phi I write psi of zeta, divided by dx square. See, dx square, from this equation dx square you take this term to the left side, 2 mu c by h cross square raised to minus 2 by 3 d zeta square. So dx square is substituted to mu c by h cross square raised to minus 2 by 3 d zeta square. Minus 2 mu c by h cross square into x minus x1, phi is shifted to say zeta. Of course, phi is shifted to say psi of zeta. Of course, this involved x. However, this is a substitution for the next step. I already have say zeta here. So this term is retained in terms of x. However, this is not x term. This is a zeta term. That's equal to 0. Now we multiply the entire equation by 2 mu c by h cross square raised to minus 2 by 3, so that this denominator will be going, and we will have this in the format d square psi of zeta by d zeta square. Minus is already there. Once this is multiplied, 2 mu c by h cross square raised to 1 into 2 mu c by h cross square raised to minus 2 by 3. Make it say 1 minus 2 by 3 as the power 1 minus 2 by 3 is 1 by 3. That turned out to be say a substitution for zeta. 2 mu c by h cross square raised to 1 by 3 into x minus x1 into psi. Now exactly this is zeta. We substitute it. The Schrödinger's equation modified in terms of psi of zeta as d square psi of zeta by d zeta square minus zeta psi equal to 0. This is a special differential equation known as the Airy differential equation. Airy differential equation, and some of the special functions you have already discussed in first semester of your study. However, Airy didn't come in those special functions. This is a special differential equation, Airy differential equation. The solution of Airy differential equation are known as Airy function and Berry function. So the solution of this equation can be written in terms of Airy and Bailey functions, and these solutions are given here. Airy function is represented as ai of theta, which is given by 1 by pi integral 0 to infinity cosine of s cube by 3 plus s theta ds. And the supplementary Airy function or supplementary solution, always referred to as the Bailey function, B-A-I-R-Y. Bailey function given by 1 by pi integral 0 to infinity e raised to minus the same term with a negative symbol for the exponent, e raised to minus s cube by 3 minus s theta plus sine of the same term s cube by 3 plus s theta ds. So these are the wave functions or mathematical functions or mathematical curves representing the system at the turning point. This is a line, say somewhere here, at this turning point. So at a point extremely closer to the turning point, because we take either the solution in region 1 or in region 2, the quantum mechanical region. So once you are considering a point, say somewhere here or say somewhere here, it is exactly represented in terms of Airy and Bailey functions. Of course, the most general solution will be a linear combination of these two solutions, but we never have an interest in this solution because it is the point at which the particle do have a momentum that vanishes, and of course that point itself has no significance. However, the solution at this point will have some relationship with the solution at this point or say somewhere here, of course for the point say somewhere here. And in all these regions we have a very large probability for finding the system. So we generally have greater interest in the solution in this regime. Similarly, we will have interest in this regime as well, or say not here, say in this regime as well, because you cannot have a classical system occupying this region, and these particles can be found in this region as long as the problem is concerned. Then there is only one possibility for a probability for finding the particle in this region. The particle in this region might have penetrated to this region. That is purely a quantum mechanical concept with no physical counterpart as long as classical mechanics is concerned. So generally we are interested in the solutions far away from the turning point, and we have generated a solution that is a solution exactly at the turning point. So we'll have to cater our interest. We'll have to identify the nature of the solutions in this region as well as in this regime that are nothing other than the asymptotic values of the solutions already written at a point closer to the turning point. Asymptote, as you know, see the solution here might be a curve something like this, and the tangent of this curve at this point will be an asymptote. Tangent of this curve at this point will be another asymptote. These asymptotic solutions are being written in terms of the WKB solutions, and we are interested in the connectivity between these two asymptotic solutions. For that, we will be writing the asymptotic value of Airy function at a point say x much less than x1. That is exactly in the region say 1 or the classical region. And of course you can write an asymptote of this curve Airy function at a point x much greater than say x1. Of course there will be a connection between this asymptotic solution in this regime and the asymptotic solution of Airy function in this regime. The same mathematical procedure we can apply for the Bailey function as well. These two solutions will give you then the connection, and similarly for the two asymptotic solutions of the Bailey function also will give you them then the two connection between the two solutions. So We will now evaluate the asymptotes of ai of theta and vi of theta. This cannot